Uh, First of all, I would like to take this chance to thank you, Vicky and Casey, inviting me here to deliver a talk. This is very the first time I've been given talk at IMS. I think last time I was delivered a talk with NUS was probably around in the year of 2000. So it was quite years ago. And this is my pleasure to be here again to talk with you on some of the work which was done together with Dr. Lika, who was my PhD student, currently is a assistant professor in Astor University. And the other one is Man Yun Wu, is currently my PhD student, and also Qingfu Zhang is my colleague. So today I'm sharing with you some of my work. This is done in the last about 4 years. So I will start with some introduction on the multi-objective problems. And I think you have heard a lot today about the multi-objective optimization or evolutionary algorithms. I focus on one simple problem today. Is on the selection problems. You know, in the evolution computation, one of the important questions we ask after the recombination, what to select. So I'm trying to aggregate these problems using a very famous algorithm named stable matching. So I will start with some of the very basic introduction that I think you have heard quite a bit today on the multi-objective problems. So multi-objective, this is the definition of either you want to maximize or minimize numbers of objective functions. Okay, so this is basically the problems we face every day on multi-objectives. So I think Professor Sugar Fan already described the TSP problem, which is a very common algorithm. Because I think if we talk about the evolutionary algorithm, the basic one on genetic algorithm, John Holland, in his book, he also used the first chapter, the first application, he used TSP as one of the example. I think if I still remember, he also used the other one on a bitstream, which Sugar Fan probably against that he used that algorithm for illustrate the beauty of genetic algorithm. He used a bitstream for a function minimizations. So obviously, that is not a good example, right? Because if you want to minimize a functions, why do you want this type of algorithm? Definitely not. But TSP is a problem you are trying to optimize two objectives. One is the traveling time, the other one is the cost. Of course, if you take a low cost, long traveling times, or you could have a high cost or short traveling time. Well, you cannot have a low cost but short traveling time, right? But however, in between, you could have many choices, okay? So it comes with the multi-objective. The other problem, I think, in multi-objective or in evolutionary algorithms, we always think, what are the good problems for this type of algorithms? This is something I think for the people like us, I've been doing evolutionary algorithms since I think it's '96. So we're all thinking until recently. I would say because of what we talked with Casey, how come in a sudden evolutionary algorithm attract all of the people's attentions? But at my time, like Professor Sugar Fan said this morning, every time we submit the paper using genetic algorithm, they all challenge one question. how your algorithm be used in real time, right? So because you cannot guarantee the convergency, so how can you be used in real time? So this is the questions being asked. But for some problems, I think this is one of the problem I like it very much. You see in your mobile phone, this is all the antenna look like. This is all the antenna go under your printed circuit board, and such that they could have a reasonable coverage between gain and bandwidth. So if you look at this one, so they try to balance the design between the bandwidth and the gain. Of course, if you have a narrower bandwidth, then you have a higher gain. If you have a wider bandwidth, then you have a lower gain. So you are trying to strike the balance. So if you look at this, if you look at this type of design, it involves tons of parameters. You don't really know. You don't really know what type of shape it could come out. But I think people in using evolutionary algorithm has been very successfully tackled the problems using for antenna design. So the idea on multi-objective is we are trying to find a set of solutions. Okay, so if we have two solutions in the Pareto dominance, the idea is saying that the solution 1 will dominate solution 2. Vice versa, if you come in these two solutions, then we will say that they are non-dominated with each other because we could not conclude which one is better than. We cannot say that solution 1 is better than solution 2 or solution 2 is better than solution 1. So instead, in multi-objectives, we are trying to locate a set of solutions which is along the parental front that consists of the objective vectors of all the parental optimal solutions. So this is the idea. So we are trying to locate for a set of solutions instead of a single solution. Of course, after you get this set of solutions, then it still comes with a later part of the decision making. Multiple decision making is also a very important areas that I think I have to admit that in the evolutionary computational area, not too many researchers tackle this problem. Some people using the counting distance, trying to measure the goodness of the solutions such that to help the decision maker to make decision. Okay, so of course, right? We will call this type of solutions extreme solution, very awesome along this side. They are only good for one objective, but very bad for the other one. So this is type of solutions, but from the parental dominance point of view, this solution, they are equally good as others. So for the, well, this is a EA evolutionary algorithm, the framework. So basically, you start with a population-based, so you pick, say, 50, 100 solutions, then you reproduce the offspring. Okay, then after that, you have to pick the solution which go for the next round of evolution until certain fitness criteria has been met. So this is a framework. So today I'm focus on one problem and one kind of algorithms, okay, on the selections. So when we produce solutions such that it could be survived, so there are two criteria in the selections. This is what we want. First, we want to obtain the blue dot, which have a very good, assuming the red line is the ground truth of the parental front. So we would like to get the blue dot as close to the red line, as close to it as possible. And also, we want to have a spread as even, as wide as possible. So basically, these are the two criteria. When you're trying to select the individuals in the term of PSO, or in the term of evolutionary algorithm is the chromosome. Okay, so those are the ones we wanted to be kept in the population pool. So MOEA decomposition. Okay, so this algorithm, I think, is the algorithm proposed by Qingfu Zhang. And this algorithm has been, in CEC 2017, has been awarded as one of the winner algorithm in solving multi-objective problems. So what it does is decompose a multi-objective problem into a number of single objective optimization problems and then optimize them simultaneously based on the weighted sum and Chebyshev measure. So basically, if this is, you minimize the Chebyshev distance between the solution and the weighted sum and optimal. So if you turn it to, you could turn it to a maximization problems. So basically, if you have a parental optimum, you could divide it into a number of subproblems in this case, based on the even distributions of the weighted sum. So then the problem in this case, it turned out to be a lump into the following in the selection. So we have in the MOEA decomposition, so the algorithm basically is similar to the very traditional evolutionary algorithm, except that it decomposes the problem into a number of subproblems, which is not uncommon, and then you take the measure. So then the problem becomes, you are going to have select a solution from a problems. The objective is to minimize the objective of the subproblems. On the other hand, the subproblems are also constructed using a set of even distributed weighted vectors. They try to make it the spread as even as possible to ensure that diversity be maintained. So, give you an example like this. If I have 5 subproblems and I randomly generate 10 solutions, so in the MOEAD, then we are trying to pick some, randomly could pick some solutions and assign it to problems, and then go for the single objective optimization, and then calculate the aggregate Chebyshev distance, and then minimize them. So in this problems, then during the optimization, the currently elite solutions might have a stronger chances to be survived than others. Okay, so in this case, for example, in this case, if I have x1, then it could be picked by this problem and this problem because it has the best measure. Vice versa, that this solution will assign it to this problems. So in this case, you will see that these 2 solutions will come dominant because they're so good. So they will dominant the whole. Dominant the selection in this case. So the traditional MOEAD, in this case, it failed in the diversity. Okay, although the result they come up is really good. We'll show you the effect later. Okay, so we formulate the problem in this case. Now we're seeing that we have problems, we have solutions. So they're supposed to have a good match, right? So inspired by the stable matching algorithm. Okay, stable matching algorithm is basically able to solve one very traditional problem called the stable marriage problems. So this is the early work of a Nobel winner by winner Lloyd Sharpley. So what they do is a problem, they're finding a stable match. Okay, it stays stable. So stable means that if I match you, then you have a less chance to be broken up. Okay? So give you an example like that is if you have 3 men and 3 women. So each of them, say, they are asked to give a preferences of ordering. So this woman 1 is man 3, man 2, man 1, and then woman 2, man 2, man 3, man 1, and this is M1, M2, M3, etc. So if we think we do a matching like that, it's okay. But okay, if like this, then it will not be a very good assignment because based on this assignment, you will see that M2 prefer W3 more than W1. And vice versa, W3, he prefer M2 more than M3. So in this case, if you do an assignment like this, then the chances will be broken. They will just one way with this type of assignment eventually. So therefore, this is not stable. Okay. So if you have something like this, it will become more stable. Okay. So the idea is like this one. Even though you will see that W1 is not M3's first choice. However, M3 is W1 first choice. So the idea is you must have, in order to have a tight bonding, you must have someone who has the desire to keep the relationship, not both. If both of them have no desire to keep the relationship will not last. Okay, so this is the idea of the stable matching. It's quite interesting. And the implementation is not difficult. So you could find it online. So this is the implementation. So you select all men and women to be unmatched. So while this is man-oriented algorithm. So when the man is still not unmatched, then you pick the woman. If the woman is unmatched, then you match them. Otherwise, you match to the current prefer the man, and then you take it away. So this is not very difficult to be implemented. So this algorithm is basically a one-to-one matching. Okay, so this algorithm also later being used in the college admission problems in New York State. So similarly to for the high school kid assigned to universities, and it also proven the chances being accepted to the kids who take up the offer and accept the offer and go to the college, the chances is higher than before. So that's why they call it more stable, and then it saves a lot of resources rather than you let students running around. You assign him to, well, someone is doing very good, he might like Yale, you assign him to a state university, something like that, right? So, and also they also apply to the hospital resident, the housing of the medical doctor, and also the roommate assignment. So this is a very interesting algorithm, and inspired by this algorithm, we think this algorithm might be useful to the selection problem in the MOEAD. So now we model the problem like the following. So basically, we say that subproblems and solution, we treat them as two set of matching agents. So subproblems has a preference list over solution. Vice versa, solution also have a preference over subproblems. So now we have to decide what are the criteria we have a subproblems. What type of solution do they want? And also, if you are a solution, what type of subproblem you want to go with? So based on that, we decide the following. For the preference value for the problem on X, basically we prefer the solution that can minimize the objectives. So in this case, for the solution on problems, we want the distance between the objective vectors and the weight vectors to be as short as possible. So the solution prefer the problem closer in the objective space. So this one is, we are trying to deal with the convergency case. This one, we are trying to deal with the divergency. So based on this design, the stable matching is focused on both divergency and convergency, and hope to strike a balance between the two. So this is an example. If you have a problem, you want to pick the solution along this side and then get you to the blue dot as well as possible. If you are a solution, you want to go to the one with the distance as short as possible to the problems. Okay? So based on this ideas, we come up with a stable matching between problem and solutions. So when we model this one, so the selection we modeled in the early about 2014, we're able to using this type of stable matching more using as a selection in the traditional MOEA decompositions. We published this work in TEC, Transaction on Evolutionary Computation, in 2014. And now we want to see the preferences, consider the convergence and diversity. And this is looks really good. This work we come up with when we compare with a number of MOEA algorithm and NSGA2 at that time. Okay, NSGA3 has not come out yet in 2014. So in terms of we come up with a UF suite, the test benchmarking problem, the temp benchmarking problem. So the MOED at that time outperformed many of the state-of-the-art algorithm in both cases. But we still find a problem. We still find a problem in this algorithm is so that in the MOP problems, the solution they find is very extreme. So yes, you can find a very good, the ultimate measure are very good, but the solution are very extreme. So this is probably is the winner takes all algorithm, the disadvantage. They did not, obviously, this one is only looking for convergency in the multi-objective problem. In the multiple objective optimization, this is not the only thing we are looking at. We also should take the divergency into consideration or diversity into consideration. So this is the case in the traditional stable matching. So the reason is because some part of the parental front can be located very easily, while the others not. So in this case, all the solutions, this is a list, right? So you have the preferences list. So this is a solution 1, for example. He preferred P1, P2, P3, P4, P5 based on the measure. Similarly, for the problem, he preferred 1, 2, 3, 4, 5, 6, etc. based on their preferences. Okay? So this is a solution come out from the MOEAD. So based on this one, you can see that the stable matching is not able to ensure that the selected solution are matched to the closest subproblems, and such that in this case, the population diversity is being affected. So we are trying to resolve this problem. We come up with another thinking. In fact, we also borrow the idea from go along the stable matching algorithm. Also, there are some further work on stable matching. Is that instead of with the complete list of preferences, meaning that if you have so many solutions and problem, they are matching them one-to-one basis. But there are some problems. It's not like that. For example, colleges, you are only given 10 choices. You don't need to give me that many, right? So therefore, we come up with the incomplete list. So based on this, we implement two versions. One is a two-level, one-to-one. The other one is many-to-one. So this is exactly the case in the stable matching with complete list, because some women and men definitely don't want some choices. So just rule them out. Why to match things like this? Because it will be unstable anyway, right? So based on this, so the list become incomplete based on certain criteria. Okay. So the research showing that if you are able to do that, it could still be stable. Your solution will still be stable. Okay. So this is our first work. We come up with using these ideas. So in this case, a matching agent does not need to have a complete preference list over all the matching agents in another set. The other one is a matching agent can only match with one of the matching agents on its preference list. So therefore, we come up with the idea, if we only keep a few most preferred subproblems on a solution preference list, then a solution is only allowed to match with one of its preferred subproblems, then we can ensure that the solution, selected solution, are matched to its closest subproblem after the stable matching. So we give you an example like this. Okay, so now we reduce the list, the preference list, to 2. So the solution is only allowed to keep 2 choices of subproblem. So with this very simple modification, you will see that we solve the problem that the traditional MOEA stable matching. So you will see the solution like this. Before we assign all this solution goes to the problem 2, 3, 4, 5. But if we only allow two choices, then obviously in this case you will see that X9 can be assigned to P4, right? So in this case, X1 to P1, X3 to P2, X6 to P3, X10 to P5. If you see before, okay, the P4, X4 was assigned to P4, even though this is so far away. But if we want divergency, we want this guy to be matched with P4, such that the divergency, you will give X9 a chances of survival, otherwise being eliminated at the very early stages of evolution. So this is the idea. So these are the 2 algorithms. So therefore, we do the stable matching with the incomplete list. So the first version we have is a 2-level. The idea is because even though we go through the first level of stable matching, though we could match, but however, there are still some solutions. They are not able to be matched because of the incomplete list that no one prefer at the first round. So then in the second round, we'll fall back to the original stable matching algorithm. Okay, so this is the first version. So this is our solutions. So you will see that our algorithm also do very good on the UF benchmarking problems, also on the MOP problems. Although obviously we are not beating them in all of the time. There are some algorithms that still perform pretty good in some cases. So like the UF4, UF5, okay. But in most of the time, we are able to do a bit very comparable with them as the speaker is saying in the morning. There's no free lunch algorithm. This is always a good explanation for not doing good in all the algorithms. Okay, so the other one, so we later evolved to the many-to-one matching. Okay, so the selection is modeled as many-to-one matching, like the college admission problems. So in this case, one college can take in more applicants, right? That makes sense, but not the other way around. Okay, we model it this way because if we model the applicant also can take more colleges, that become a many-to-many. That will be too difficult for us to handle in such a case. So we modify the problem. We modify the problem to many-to-one. So in this case, each solution can only match with one subproblem. Each subproblem can match with more than one solutions without a limit. And the quota, we say a quota, depends on how many places you have, right, in the terminology of college admission. So in such a way, we ensure the unmatched subproblems caused by the incomplete list, given the matching opportunities to other subproblems. So in order to make sure that when we do this type of matching, it's also stable, we have the following conditions. Okay, so a matching to many-to-one matching problems with a common quota is called stable if there does not exist any pair of subproblem and solutions where P and X are acceptable to each other but not being matched. Secondly, X is a match or it prefers P to its subproblems. That's also no good. And the common quota has not been met, but P prefers X to its at least one assigned solutions. So this is a condition we try to avoid. So this is the implementation. So in the first step, we randomly assign the unmatched solutions to the favorite subproblems. And then in the step 2, and then we remove the problem from the X preference list. If the subproblem is greater than the quota n, then we need to find the substitutions. Okay, so how do we make the substitutions? If we have more than solutions, so the whole idea, if you have the assigned solutions more than the quota, you have to remove one. Which one to remove? So this is the idea. So we chose the subproblem that have the largest of matched solutions. It means that the subproblem is so popular. Everyone picks it. You got to remove them. Remove some from it. Okay? So that's the idea. So the other one is if the subproblem with least preferred solution holds the worst rank, then this is the one we are removing. So this is the algorithm. I think I try to walk you through the idea, how it works. I think the algorithm probably is difficult. For example, we have a problem like this. We have an incomplete list like this. Okay, this is a two-level, the one I just showed you. Okay, the two-level. Okay, so this one in the second level, x4, x2 is assigned to p4. And if we do a many-to-one matching, in this case, the P1 will be able to have two candidates, X1 and X2. And then X3 are assigned to P2, X6 are assigned to 3 because of the many-to-one matching. Okay? So how do I come up with this assignment? You see that. Okay, this is a problem matrix. That is the preference list for problem 1, 2, 3, 4, 5. This is a solution 1, 2, 3, 4 to 10. So basically, this is a problem 1, 2, 3, 4, 5, and its associated solutions. Similarly, this is a solution, and this is an associated problem for them. So the first step, remember that we just propose x1, go through the list assigned to problem 1, x2 to problem 2, x3 to problem 3, and then 2 to problem 2, 5, 6. Okay, now the quota is greater than 5. Okay, so we have to find a substitute problem. So in this case, we see the problem 1 and problem 2, most unmatched one. So we get a P2 with the worst one. So we remove problems, the solution 6. We select P2, we move that. Okay, so in this case, this is being removed. So 3 to 7. Again, this is greater than 6. We remove the 3. So go to problem 1, the 8. Well, this is the worst. So we remove them. So in this case, you will see that we try to strike the balance with the solution assigned to the problem. So 1 to 9, we remove them. 5 to 10. So we pick the one with the worst case. This case is 5. We remove it. Okay. So then we go to the second round. So that second round in the solution 3, he won the problem 2 in this case. So I remove the solution 4. So this case 5 here, I also remove them. 3. Okay, I also 7 in this case. So become 6. So in this case, 7 original assignment will be eliminated. Okay. Similarly, you see that on the 8, 9, 10. So then we come up with the assignment I just shown you. Okay. So therefore, based on this idea, I'm able, based on doing this type of mechanism, I'm able to come up with the matching. The solution is like this. So this is the one I got eventually when I'm dealing with the incomplete list. So you see that if you have an incomplete list, you go through 2 rounds of assignment, then you will have a better assignment of solution to problems in a more diversified way than before. Okay, so you will see that this is a very key parameter for the R, the incomplete list. How large or how small? So you will see that the effect, if R, you will see that the instance is very sensitive to the setting of R. If R is too large, then it becomes the original incomplete list. If R is too small, then the diversity is strengthened. So, well, you will have to sacrifice the convergency. So how to set R? So you will see that this is different case. This is the original one. If we set R equal to 3, then here we could only allow 3 go to the problem 1, 2, 3, and then we maintain some of this. And if you allow it to 2, then you have one more survive in this case for diversity. If stable metric equal to 1, then you will have a very diversified allocation. So it comes to a problem. That's always, I think, it's the idea you always get. We want this parameter to be adaptive. Okay? So therefore, we come up with an algorithm. Again, we come up with the algorithm for the adaptive R. Okay? So the idea, you will see that the problem 3 to 4 always get the solution x2 allocated and x4 allocated to P4. It's mainly because these two have so much contribution on the convergency. Okay? So a straightforward way is to overcome that, is to reduce the preference list. Then you can eliminate this kind of problems. Okay? But when this parameter be adjusted, be set it to larger or smaller, right? So we have to show that. We have to try out from step on the so-called online monitoring. So what we do, we come up with the following idea as well. So we introduce the concept of so-called local competitiveness. So we test them whether the solution around the problem, sub-problems, are they competitive or non-competitive? Okay? So the X is locally competitive solutions if they represent a representative solutions in this label, which is dominant by X. Then otherwise, we call them locally non-competitive solutions. Okay? So the idea is to test whether there is a competitive solution in the regions. If there is one, then we stop. So how that being work? So I also show you an example. So the first round, we assign solution x1 to P1, x4 to P, the closest one, x4 to P2, x7 to P3. This one, they have no solution, so we do not assign representative solutions, and then extend to P5. After that, then we maintain the R as the maximum likelihood, so x1. So in x1, we see the solution. We have x1. Okay, so x1 is not dominant itself, so we name it as locally non-competitive. So we increase the neighborhood from P1, P2. So in that case, we have x4 and x1. Then x1 become locally competitive because it dominates x4. So we set the R equal to 1. Similarly, R2 and 3 have the same case. So in this case, the list for 1, 2, and 3, the R setting is equal to 1. For the x4, you will see that the label we have x4. The label we have is 1, so it's P2 only. So, and then we increase it, P2 and P1, we have x4 and x1. So x4 is locally non-competitive because x1 dominates x4. And then we increase to P3, we have x7 included. But x4 dominates x7, so x4 become locally competitive, and then we stop. So R4 in this case, we set it to 2. Similar for R5. So for R6, so for the x6 here, so we start with the P2. So P2 and P4, okay, x6 does not dominate x4. So x6 is non-competitive. So we increase it, P2, P3. So we have x6 dominate x7. So x6 becomes non-competitive. We stop. So x6, R6 equal to 1. So etc. For x7, we will see that X7 is locally non-competitive because we have the X1 and X4. So we increase the populations. So we have X7, X4, X7, so it's non-competitive. So then we increase it, 2, 3, 4. So X7 is still no good, etc. So X7 is no good all the way. So it become, the R become 5. So based on that, based on this kind of mechanism, I'm able to set the list of R adaptively. Depends on the conditions of the population as well as the chromosome. So similarly, we come up with a list like this. So this is the algorithm. The first one is determine the representative solution. The second one is gradually increase the non-competitive label size in order to make it adaptive. Okay, so this is the algorithm. So this is a trading of the setting of the R, okay, in different subproblems. So we test our algorithm on many problems. In the MOP1, you will see that we test it with 9 algorithms. Or we have the hypervolume one. We also include NSGA3. Okay, so NSGA3 is supposed to be the state-of-the-art multi-objective problems. So you will see that the traditional stable matching problem still suffer the same problem we mentioned at the early time. You will see the solution we found is much more diversified. Okay, but it's also similar. Those are also good. So the other problem, NOP2. So you will see that our traditional one, original one STM is no good. NSGA3 also has similar problems. Okay, so because all these problems is looking for convergency all the times, did not take the divergency into considerations. So you'll see that in our case, like this. Similarly, MOP3, we are also doing very good. So similar, you see these two cases, they all get for those convergency-oriented algorithm, they all don't do very good. So for the broken part, you will see that NSGA3 no good. So we are able to cover some. Okay, so this one is also, but in fact, we're also seeing that the adaptive one and the 2-level perform very similar, very close to behavior. Okay, so this is a MOP5. Okay, this is a MOP6. You will see that we cover the surface much better than the others. Similarly, NOP7. So for the 3 objectives, okay, we're also doing a bit better. 5 objectives, 8 objectives. So we are doing, in this case, we are doing the pretty good, the 2-level one. But the many adaptive one, many to one don't do very good when the number of objective being increased. So this is, and 10 objectives. So in order to conclude the talk of today, that I think we have tried to a kind of new way to do the selection between the subproblem and solution. I think this is interesting, and that could be used in many other matching work. Like you, I think the presentation before that is matching the interviewer to the one I think is using this algorithm seems to be more robust if you are able to decide the matching criteria. So we, based on the stable matching, we come up with two kind of algorithms, and then we are able to come up with a dynamic control for the length, the how many places be used. So I think those are very interesting. So what are the future work? We're still thinking of allow unique solution to be matched with more than one subproblems. That will improve the convergency, and also we will working on the preferences. In order to make this work, in fact, I think in many of the evolutionary algorithm, in my personal opinion, I think the objective function is very important because that is very costly as well. Every round we have to go through the objective measurement. So So those are the references. So the first one is the one I mentioned to you, is on multi-objective optimal antenna design. The WEC 207 is the MOEAD, the original algorithm. And the reference 3 is the work I do. I'm inspired by this work, college admission and the stability of marriage. So this work is done on 1962. It's nothing new. So 4 is the one we first applied this work to the stable matching to the selection. And Ching-Fu later come up with the multi-objective problem decompositions. And this one with the incompleteness in 1999. So they come up with the stable matching and prove that this is still robust, okay? And this is our first work on the two-level stable matching published on the SMC conference. And then this is a college admission with lower and common quotas. It's a 2010. So this is our final work, evolved from the SMC conference work, become the transaction paper. And thank you very much. This is the end of my presentation. Thank you. Questions? No.
So the running time is very minimal.
Yeah, this one is much faster. Yeah, pretty fast. It's not. The algorithm is easy. First of all, you look at the algorithm; it's very simple. So it's not a really big problem. Well, as I said, right? I think the major burden is on how you decide the metric to measure how good the relationship between the solution and the problems. If that measure is very complicated, then the whole thing, the whole advantages is gone. So that's my personal view on this.
So is this used in college admissions?
Yeah, it's being used. It's being used, the algorithm being used for many. In fact, they also applied it to the stock auction. When people bid and buy, they try to match the bid and buy things. So this algorithm, is very, very interestingly. I think I consider simple, easy to understand, but effective. Yeah.
And there's no question of optimality. Is this a really?
It's being proved. It's being proved. I think they proved that. Yeah. Yeah.
The stable matching, if the man proposes and the woman accepts, the solution is different from the woman proposed.
Yes.
So in your case, is it symmetric in that sense?
No, it's not. You see that mine is not symmetric. No.
No, what I meant is if you use one preference to do a proposal first, and then if you consider the second objective for the proposal.
No, I think we will come up with different. Right. We will come up with different solutions. They won't be symmetric, but they still be stable. They still be stable, but the solution might not be symmetric. Correct? Yes.
If you try many objectives.
Yeah, KC now challenging on the kind of very challenging problems nowadays. Right? Now, easy community started to work on the many objectives in this way. I think we all come to a consensus. The problem at least over seven is the minimum, right? I think 7 is the minimum. So when it comes to many objectives, surprisingly, there are two algorithms working reasonably good without changing anything. This is one of it. NSGA3 is also another one. But ASU also do a analysis on the many objective optimizations. His argument is similar to the low-frequency algorithm. He said that some algorithm is doing good on certain number of objectives, but some good at others. It cannot conclude any single algorithm could outperform any others. So when it comes to many objectives, it's very challenging. And also, I think people people also need to, I think, to visualize how good your algorithm is also difficult instead of just compute the hypervolume or IGD values. So this is the challenges for this type of, I think, yeah, many objectives nowadays is very hard, and the algorithm I think is also doing pretty good, doing reasonably good, but not for all the problems, not for all the many objective problems. Yeah. Probably, yeah.
So for multiple objective problems, is it built into the system? Like if I say this objective is the most important, this one is second, and that one is the third most important, and so that would presumably change the choice of the mental prime, right? Is there something
Yes.
that can build into the...
They have no discrimination. They have no discrimination against objectives, right? So.
But in practice, that may be the case. So what
Correct.
do you do in that case?
I think this different algorithm can handle the preference of the different objective.
You could.
Also, all these algorithms can be amended.
It can be. Yeah, we have proposed algorithms to handle the different preference of the different objective. So okay, see one at the highest priority, then objective 2 will be second highest priority. So what you need is that you actually try to optimize objective 1 first, then follow the objective 2 layer by layer.
I think in the stable matching, if man proposes first, then man gets the best choice and woman gets unresolved.
You could do that type of modifications, right? You can. Well, of course, the problem is, if you know in advance, yes, you could do that. But most of the time, you don't know, right? Most of the time, I don't know. Until, put this way, most of the time, in practice, most of the time when you have this type of problems, you come up with a solution and then you present to the decision maker. They say, this is what I want, and then you have to go back to rerun the algorithm. That is usually the case, right? If you know in advance, of course, that's easy, right? You just give them more weight among all others, right? But in the benchmark problem, we don't. First of all, in our benchmark, I think in our community, we always go along this type of benchmark problems. So that's easier to measure the performance. But when it go to industry, put this way, when you go to something in practice, then I think the idea is whether you could come up with a reasonable solutions proposed to industry, right? I think I remember I think about 15 to 20 years ago, a guy from Boeing, he's very successful using the evolutionary algorithm in designing some of the turbine. So those problems is very difficult to come up with a good solution because the space is so high that it's not, sometimes it's not easy for you to tell which part is very crucial to the design until you see the design. Then you see, oh, it can be like this. Then which part could be optimized. So I think it's similar to the talk before. Usually is that, I think in practice, it's okay to come up with a initial design. Then later, probably nowadays, well, even in many scheduling problems, you all work on that, right? So the latest part is mostly manually to adjust the final leftover. So I'm not saying that this type of algorithm can solve all the problem and provide you a final solution. My gut feeling is they can provide you a solutions and that could solve the initial, I would say 60% of your problems. Then you work on the remaining 40% of the problem. This is my gut feeling anyway. Yeah. Okay.
Any other questions? If not, let's have the speaker again.
Thank you.